Okay, so guys, this is, well, let me help you understand the weirdness of today. So, topics for today become the titles for your notes, right? And then, guys, the date today is the 14th. So you're dating your notes, 12/14, but then you're going to put a slash, and then also January 4th. So guys, this is the way this is going to go down. This is typically material that we teach all in one day, and we will never do that again. Miss Call and I are always working at improving our craft. And guys, frankly, she and I got together yesterday after school once we had done this with our A-Day classes. And frankly, we looked at each other and said, what on earth have we been doing for all of these years? Because guys, we are only going to get into about a third of the material that we normally would cover today. The reason that we're breaking it up is because the first third is foundational. The last 2/3 are application. And you'll never remember that after Christmas break. So we said, let's do the foundational stuff today and then come back and do the rest of it later. We will never teach this all together ever again. I don't know how we did that in years past. So guys, today is going to be brief. We need to add one more skill to your tool, one concept and one skill to your toolbox. Christmas. Guys, what that also means is you're not going to do all the homework today. You'll see in a moment that the homework assignment for today is huge, but you're not going to do it all, and you'll see why when we're done. Okay, so guys, starting the clock, 9 minutes. We can do that, right? No. Introduction doesn't count, right? That's like the coin toss during the football game. They don't start the clock during the national anthem. I did?
Yeah. You went 7 to 8 to 9. Yeah. Okay, we'll start and we'll be there.
Give me 8.5.
Okay. Somebody, can we actually time it?
No, you don't need to time me because, no, watch. As the video records, oh, but wait, the video's already started.
Yeah.
It's okay. Oh, Santa save us. Okay, ready? No. Okay, go. So guys, it goes like this. Please don't write this down. So guys, in the coming days, and we've sort of flirted around the edges of this a little bit, we're going to talk about some interesting stuff. Guys, I love this stuff. It really, in a weird but real way, really will change your perception of your world, because all of a sudden you're going to know the whys behind some whats that you'd never even considered. But guys, the thing that you're going to find interesting is that the whys behind these whats all lead back to one central answer, which not surprisingly is the polarity of molecules. Guys, the thing that you need to be able to appreciate at the end of today, remember we talked about this, question number 19. You've got to be able to look at molecules. Hey, Ethan, why don't you just go over there? So, guys, you understand that we need to be able to look at molecules and go polar, non-polar, polar, right? And how do we do that? What's the two tests? Dots on the middle, different atoms around the outside. Guys, here's the extra layer to the onion today. You've got to be able to look at two molecules that are polar, and you've got to be able to say, this one is more polar. And it's not hard, but we need to get there. So guys, first of all, why do we care if molecules are polar to begin with? And guys, the answer is this. And again, I'll tell you when to start writing this down. So here's where we are. Right now, we get polar. That one is, that one isn't, that one is, that one isn't. We know how to draw the arrows. Well, guys, as we draw these arrows, the reason that we care is not just because they're polar. What we really care about is how polar molecules interact when you get them together in large groups. So if you have 1 billion polar molecules, what do they do when they all get together? And guys, the answer is simply this. These are polar molecules, right? Water is a polar molecule. You've seen the arrow drawn in this direction. Well, guys, what happens if you get polar molecules together? They stick. But guys, look at the way they stick. Why do they stick red to white? This is the negative. So the red is the negative dipole, right? The arrow. And they stick together, negative dipole to positive dipole, and then they go positive dipole to negative and negative to positive. But notice they can't stick together positive to positive or negative to negative. It always alternates. And if you get enough of those together, they do this, and you get liquid water. And then if you slow them down enough, they can't sneak past each other anymore, and you get ice. But guys, that's the whole idea. And this is the interesting stuff that we're going to talk about. And it's all based on the fact that polar molecules stick together. And guys, your entire world is defined by this. Why is it when you cut yourself, you don't bleed out? It's because there are these magic little molecules that float all throughout your body. And when they get exposed to air, their polarities change and they lock together. And what do they form? A scab. Guys, our bodies are these amazing polar systems that literally live and die based upon the polarities of molecules. It's fascinating, crazy stuff. Guys, why does your flesh literally die when you get frostbite? And the reason is because all the liquid molecules inside your cells freeze. And when they do, they expand. And when they do, your cells burst and your flesh dies. Guys, everything inside your bodies hinges on crazy stuff based upon polar molecules attracting each other. So let's dig into this a little bit deeper and talk about a new term. And guys, this new term is actually intermolecular forces. Don't write it down yet. I know you feel it'll be there in a second. So guys, the question is this: what do polar molecules do when they get together in big groups? And guys, the answer is they stick together. They attract. So guys, and this you do want to get in your notes. Guys, polar molecules, when they group together, they attract each other. And as we understand, these attractions are positives to negatives. By the way, guys, as you're writing this down, if you want to have an experience that's bordering on the spiritual, go home tonight and Google blood clotting cascade. The things that happen in your, and it is about polarity and intermolecular forces, but guys, the things that happen inside you, it's like a 7-step process that causes your blood to clot. It is so, and form a scab. It is so interesting. Check it out. It's pretty neat. So, guys, polar molecules gathered together stick. They stick together positives to negatives. We call these, this is the big idea, intermolecular forces, or IMFs. So guys, in order to understand this, you need to know that the prefix inter means in between. Intra means within. So if you play intramural basketball, you play against people from your own school. But Shem, as a varsity basketball player, plays against other schools. And guys, they actually used to call varsity athletics intermural sports, because you play in between schools. Mural means school. So guys, intra, within, inter, in between. So these are forces between molecules. But guys, the thing you need to know about these forces is they are weak. Intermolecular forces are not strong. They are about 1/10 to 100th the strength of a covalent bond. But guys, please do not confuse weak with unimportant. They're wildly important. Our very existence depends upon them. But guys, they're not very strong individually. But the thing that's interesting about these guys is they all don't have the same strengths. Not all intermolecular forces are the same strength. Some of them are stronger and some of them are weaker. So what determines the strength of an IMF? the polarity of the molecule. And this is where we're headed today. So guys, the more polar the molecule, the stronger the intermolecular force. So why does water boil at such a ridiculously high temperature? And why does alcohol boil at a lower temperature? They're both liquids. And it's all about their intermolecular forces that depend upon polarity. You guys all caught up? Okay, so guys, all of this then begs something that I think you're going to be really good at because we have a good English department. Guys, as you do this, you are going to be developing cause and effect relationships. This is true, so this is true. Water is very polar. Therefore, it has strong intermolecular forces. Therefore, it boils at a ridiculously high temperature. Guys, 100 degrees Celsius, 212 Fahrenheit, where water boils, that's an amazingly high number. That's a really, really high boiling point for a liquid. So guys, those are the kind of things you're going to be developing, are these cause and effect relationships. Now guys, what did they teach you in English? When you're developing cause and effect relationships, what are the words that you use to lead your reader through your reasoning? If then, if this is true, then this is true. Others? Because. Others? There's one that I really encourage my AP students to use. Guys, the word is therefore. Therefore is the big one. Guys, you are going to be using therefore a lot. Did they tell you this in the English? This changed the way I read. I remember somebody in college told me, anytime, and this is corny, but anytime you see the word therefore, you should always ask yourself, what is it there for? Seriously. No, and it seems corny, but guys, understand that if somebody's using the word therefore, they're developing an argument. This is true, therefore this is true, therefore this is true. And in order to understand the argument, you should ask yourself, what is the therefore? Therefore, what are they saying and where are they going? What are they saying and where are they going? And guys, if you want to see a really interesting example of this, and read the book of Romans. Guys, Paul is a master of the word therefore. And anytime you read that word, go back and reread the previous chapter, and you're going to go, holy smokes, this guy should have been an attorney. Because literally what he's doing is he is creating a logical argument all the way throughout the book. He uses, but a lot of the chapters in the book of Romans begins with the word therefore. The whole book is an argument. It's really, check it out sometime. It's good stuff. Whether you think that stuff is scripture or not, it's good writing. Go back and check it out. So, guys, this is the thing. This is weird. Therefore is kind of a big word, right? Did you guys know that there's actually a mathematical symbol for the word therefore? It's 3 dots. Use it. You guys know that? I actually, right now, I'm doing this with my AP students because you got to learn to write very concisely in AP because you don't have a lot of time. So guys, as you develop arguments, feel free to use the triple dot. It means therefore. All right. So guys, this then is where we are, and we're just about to wrap up. So it goes like this. Guys, here's the logical progression. Molecules are polar. Therefore, molecules are polar, therefore they attract each other. What do we call those attractions? Intermolecular forces. And guys, after Christmas, we're going to talk about all the crazy stuff that's true because of this. But there's one last thing we need to do and we're done. And it's this. Guys, we need to figure out how to figure out, yeah, these 2 molecules are polar, but which one's more polar? When we're done with this, we're done. 4 minutes? How am I doing on time? But we did have a scripture lesson. That buys me at least 3 minutes? Huh? Speed time. So guys, do this. Oh boy. Today, without drooling, not very fast. So guys, this is the end of the day. You're still going to get your homework done. It goes like this. This is how we're going to start after Christmas. Guys, we're going to look at molecules, and we're going to do the therefores. This is true. Therefore, this is what's going on with intermolecular forces. Therefore, this is how these things behave. So guys, to do this, we need some Lewis dot structures, and you want me to hurry, so let me give them to you. We're working together here. So guys, this is CH4. The hope is that you can look at this and go, that guy's, don't draw that. That guy's tetrahedral, right? We'll talk polarity in a minute. Now let's hop over to water. You'll be better served if you draw it like this, because it's bent. What's that? And then guys, in the middle, we're going to play with this after Christmas break. But guys, this is actually one of many alcohols. This is not the alcohol that is in beer and wine and things like that. If you added another carbon to this and made it CH3CH2OH, that would be the stuff in beer and wine. This is actually what is called methanol. You drink this and you go blind. You add a carbon to it and you get drunk. It's just different alcohol. Looks like this. You guys know about that from your history classes, right? During Prohibition, when people were making moonshine, sometimes they made their stills out of wood, and the wood would leach methanol into their moonshine, and people would drink it and go blind. Yeah. But guys, what does this molecule look like three-dimensionally? If you could almost picture building it, can you see that this is looking pretty tetrahedral, and this is looking pretty bent? It's sort of a bringing together of these two. It looks like that. You don't need to draw it, but that's what it looks like. It's cute. Okay, so now guys, this is what you got to be, this is your homework today. What I'm about to do with you is what you're going to do before you leave in homework. So guys, starting on the left, let's talk polarity. Question 19, are there unbonded electrons on the carbon? No. All the atoms the same? Yeah, nonpolar. Right? See how 19 becomes useful to us? Now, guys, let's do this. Let's go to water. Polar? Yeah, it fails the dot test. But now, guys, let's go look at this other guy. Run, Shem, run. So, guys, let's look at this middle guy. Talk to me about why that carbon is polar. These aren't all the same. Hydrogen, 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 oxygen. So it's going to be polar there. Guys, why is it also polar on the oxygen? Dots. So guys, now we have two molecules and we know they're both, this one's not. These are both not polar, or they are polar. So now guys, this is our challenge for today, and this is the homework. Which one of these is more polar? And guys, in order to know, here's what you've got to do. You're going to do this with me. In order to figure out which is more polar, we need to know what the polarities are. To know the polarities, I love that you're grabbing your periodic tables, but here you go. Guys, and I know, in order to draw the polarities, you need the electronegativities. Whether you choose to write them in or not, let's do the polarities of the bonds. So guys, which way do the carbon-hydrogen arrows point? Towards the carbon. Actually, let's do with a simple one first. Which way does the hydrogen-oxygen point? Towards the oxygen. And then the other one is polar that way as well. What is the overall polarity? This way? Okay. Now guys, looking at the more complicated one. Carbon and hydrogen. Carbon's 2.55, hydrogen's 2.2. Which way do those go? Towards the carbon? Yeah. Okay. Now guys, what about the carbon-oxygen bond? Oxygen's 3.4, carbon's 2. Towards the oxygen. And then guys, what about the oxygen-hydrogen? Towards the oxygen. All right. So now guys, let's do the overall polarity for that middle molecule. And look what we got. We got coming together, going to the right, going up, what's the overall flow to that molecule? Can you see that it's this? Yeah. All right. Now, guys, once you've done that, this is where this becomes new. Now we're ready to answer the question, which one of these is more polar? We know that they're both polar, but which one is more polar? And here's the way you do it. Go to the arrow, the big arrow, and you can circle if you want, but you don't need to. Guys, what you're going to do is you're going to look at the two bonds, or as many bonds as, you're going to look at the bonds next to the big arrow, and you're going to do some math. And you're going to figure out the polarities of these arrows. Here's how you do it. This is 3.44. This is 2.2. Subtract them. And when you subtract these two, you get 1.24. So guys, that difference is the polarity of the bond. Just a second, Bailey. So what about this bond? Same thing. Same atoms, same polarity. Now, guys, let's look at the middle molecule. Oxygen, hydrogen, right? We've already done the math. This is 1.24. But, guys, what is the polarity of that other bond? Because we've also got to look at this carbon-oxygen bond. That would be 3.44 minus 2.55. That would be 0.89. Now, here's how to know the one that's more polar. The one with more polar bonds will be the more polar molecule. So here we have two 1.24s. Here we have a 1.24 and a 0.89. So guys, which one's more polar, the water or the alcohol? The water, because the values are bigger. These numbers are bigger than these numbers, so this is the most polar. This is less polar. But guys, what about CH4? That's the very least polar, because that dude's not polar at all. And guys, when we get back after Christmas, we're going to do the so whats, because you're going to find out these molecules behave radically differently based upon their polarities. Stop the clock. I'm not even close, am I? You guys need a better teacher. You guys know I say that to my children all the time. Dad, this isn't fair. This is stupid. Cody, you know what? You need a better dad. No. Yeah.
So why do you put the arrow to the oxygen
on which one? Oh, on the middle one? Because the overall flow is this is flowing in, but then it's all flowing out, if you will, into that even stronger oxygen. So the whole movement is that way. Yeah, technically, Bailey, this probably should be more like that, but so long as you get it close, you're good. Okay. Hey guys, let's talk homework. You're still going to get this done. We got 20 minutes. Here we go. Look at assignment number 2. 3 pages. Just look. Guys, page number 1 with all of those arrows. Do you see it? The left-hand column, here's the polarities. The middle column, here's the intermolecular forces. And then the right-hand column's a bunch of stuff we ain't talked about yet. You can't do it. Now, guys, go to page 2. Here's what it says. For each of the following compounds, draw the Lewis dot molecular structure and indicate the molecular polarity with an arrow. Then, circle the more polar molecule, just like we talked about on the board, but it won't be least, less, and more. It's just one's greater than the other because you only got sets of 2. So you're just going to circle the one that's more polar going through what we did. Now, guys, look at the last 2 examples. Methanol, CH3OH, it's on the board. But guys, the one off to the right of that, diethyl ether. I would never expect you to be able to come up with the structure of diethyl ether. Copy it out of the answers online or on the wall, but you've got to be able to draw in the arrow and figure out the polarities. Then guys, the last 2, acetone, which is actually fingernail polish remover, and then the one on the right, which is propanol, which is actually the propellant in hairspray. Guys, these two, I also don't expect you to be able to come up with, and do be careful, as McKenna pointed out. Guys, this is what, no, sorry, oh yeah, so this is what my computer did to acetone. Be careful, it got messed up. So realize there should be a carbon in the middle of each of those and then hydrogens. So guys, turn to the last page. Regarding the molecules you just drew, answer these questions. You can't do that.